This conference will now be recorded.
All right, I want to thank you all for your time today. Very excited to get the opportunity to speak to you about cold climate design for variable refrigerant systems. I'll apologize in advance. I'm working through a little bit of a COVID fog, recovering just fine, but the after effects are a little rough. So if I start to space out, somebody just reach through and smack me. A little bit of my background, as the introduction said, my name is Mike Hudson. Little of my background, I got started in the industry about 27 years ago. Got my start on the refrigeration, primarily industrial and marine refrigeration side of things. Got the first introduction into variable refrigerant systems pretty much right when they came to the US in 2001, 2002, so coming up on 20 years there. Excuse me. Give some perspective on that puts that equipment, my first exposure to variable refrigerant systems, they were actually still R22 equipment, so give a little date perspective there. Quite a bit obviously has changed over that time frame, mostly to the good, and we've learned a lot of lessons. I've been intimately involved in learning a lot of stuff that people thought wouldn't work that did, but probably more importantly, learned a lot of stuff that looked good on paper and didn't work. So my goal today is to try to highlight some of the best practices learned in cold climate applications and discuss some various strategies that can help ensure satisfied clients when applying variable refrigerant systems in cold climates. Not sure who's echoing, but if everybody could mute, would be great. And feel free, if I cover something and you want to chime in, just unmute and don't hesitate to ask questions. I love questions. All right, so as I was discussing agenda today, my goal is to talk about some of the best practices, things we've learned over the years, discuss some of the strategies for taking care of VRV, VRF, variable refrigerant systems in cold climates, including supplemental heat, alternative heat, doghouse applications, and the latest enhanced capacity systems that most manufacturers have some option for. So low ambient applications, what are the issues that we're looking at here? First and foremost, when you're applying any HVAC system in cold climate, you got to consider the equipment location, keeping it safe, keeping people safe around it, preventative measures to increase the longevity of its life cycle. We have to consider the capacity D rate on heat pump systems, low ambient conditions, as well as manufacturers' minimum outside temperature ratings for that equipment. What happens to your heating capacity during defrost is also something we need to look at, as well as the dreaded catastrophic equipment failure and how to plan for that. First and foremost, one thing that should never be left out in cold climate, anywhere that we get snow, and typically where it gets cold, or we get some of that, you want to make sure that you have variable refrigerant systems put up onto a stand, whether that be manufacturer supplied accessory, third-party option, or something that you have field fabricated. Every manufacturer's guidelines are pretty similar, that you want to plan to have good clearance above any expected snow or drift for the region that you're working in. From a safety standpoint, You also have to consider if you need to do any mitigation for the defrost. The unit's placed in an area where defrost water is going to shed and ice up and cover a walkway and become a hazard for people walking, or even on a roof. Is it going to freeze up, create safety issues for people working on equipment or traveling on the roof? To that roof. Various ways to handle that with um, temperature actuated heat trace, whether you've got to trace it to a drain so that the water can continue to drain away or drain into the soil. Those type of strategies are things you want to think about as you're placing your equipment. Also, you have to consider the location as it pertains to wind, blowing snow, hail in cold climates. My experience with multiple manufacturers that I've been involved with is that everybody pretty much has the same blanket statement of place that unit outside of the prevailing wind direction. Now, again, that's great on paper, not necessarily always possible on every application that you're going to work on. So to hamper that, some of the time these go onto roofs and you don't have any wind protection there. And that's when you need to consider the manufacturer's options for either field installed accessory or field fabricated accessory of snow baffles, snow hoods, hail guards if you're in an area where hail can damage the coils, as well as implementing strategies if you're in somewhat milder cold climates where heavy snow can set on a unit, but maybe that unit is in an off cycle and set back, and that snow is going to sit on top of the unit, melt down into it. Most manufacturers have some sort of snow blow setting that you can set on variable refrigerant systems. So if it is in a thermal off cycle, it will cycle that condenser fan on periodically to try to blow snow off of it so that you can try to prevent any excess ice buildup leaking down into the fan blades, causing damage to the condenser blades or motors. So to understand why we're talking about auxiliary heat, I think it's obvious for most of us, but first thing we're going to talk about is variable refrigerant with cooling. It kind of all factors in from the whole comfort strategy here that typically you're using this so that you can also have cooling in the summertime in most of the colder regions. So why are we talking about cooling when we're really talking about auxiliary heat? There's a tendency in variable refrigerant systems to just assume that they're kind of a magic bullet and that oversizing isn't really a problem. Now, there's some truth to that. You can get away with it. They are incredibly flexible systems. But when you consider your cooling loads in some of these areas and what it takes to end up grossly oversized on the cooling side, which can create operational issues for equipment and reduce life cycles of these variable refrigerant systems, it doesn't take too much to get oversized on the cooling side. When you look at Ashrae conditions around the US, a 20% reduction in capacity on the cooling side for your average 8-ton unit, it has to get to 118 degrees outside. Now, no state in the lower 48 or Alaska or Hawaii that I'm aware of has an average temperature of 118 degrees. So when you take that and switch it over to the heating side, anybody want to guess what it takes to lose 20% on the heat side? I'll give you the free answer. It's about 9 degrees outside on your average 8-ton that you would be a reduced 20% capacity. And you look at that across the entire US, that's a lot of areas that could benefit from a little extra heat. As I said, oversizing is possible with variable refrigerant systems, but you still have to consider the overall impact and the pros and cons of it. If you end up grossly oversized, especially on the cooling side, you can cause harm to that system, make it have a harder life because it's running at low operating conditions for an extended period of time, which will result in short cycling, owner discomfort, possibility of oil control issues. So the same kind of rule applies as with every other heat pump system that I've worked with over my years. Is you want to make sure you're covered on the cooling side and take a look at the cost benefits of how much you can increase the sizing on the heating side. If you go too much to the heat design and size for that, you're adding cost to the job and potentially harming the equipment in the long term. So how do we decide where the best points are to apply auxiliary heat? First, you have to look at balance points for that system to your design profile. Now, every manufacturer has capacity curves published. You need to know your manufacturer because some of them derate the outdoor unit, some of them derate the indoor unit, but you should be able to get the information to plot your load profile against the actual capacity capability of that system at your design condition. Once you have that information, you can run that to see where your balance point is. Now, this is an average 10-ton unit. Given your load, no load at 65 degrees, and your design load, in this example, at minus 13, you plot the outdoor capacity of that, and the lines intersect at about minus 4 degrees outside. This would be your balance point, and we'll talk a little bit more about this specific to both supplemental and what we call alternate heat. As a general trend, the variable refrigerant system balance point is going to shift higher as you reduce the capacity of that outdoor unit. So as I said, you can size to hit 100% of your requirement at your design condition, but you have to look at the factors of how oversized is that on the cooling side, and is the juice worth the squeeze, if you will, on the cost of the project. So adding more equipment adds more indoor gear typically, adds more outdoor gear, more electrical, more weight, all of those factor in. So take a look at your options, and this option we're looking at a 6-ton, a 10-ton, and a 4-ton. Your 10-ton, your balance point is at that minus 4 area. If you went to a 6-ton, if it covered your cooling load, the juice may be worth the squeeze depending on what your auxiliary heat source is to go to that smaller capacity outdoor unit and move your balance point to a higher position there. In this case, it's about 10 degrees. So not adding a whole lot of extra heat at that point, but reducing a lot of upfront costs. So we'll talk more about these in depth as we talk about these cases one-on-one, but balance point for a doghouse application is a little bit of a special case. For balance point for the doghouse, the minimum outdoor capacity that can meet the design load is what you're going after, and that is not the point where it intersects, but that your outdoor unit is capable at some point of meeting that entire load. And again, you have to look at whether the juice is worth the squeeze given your load. Plot your outdoor capacity curve and find the point where it correlates to your load, and that is your balance point. So you can see here that is 5 degrees in this case of this 10-ton. Just to reinforce this a little bit more, again, your 14-ton, you're covering your entire load, but you have to consider the cost and the ramifications of operation of that system in the long term. You've got your 10-ton that your intersect is 4 degrees, but that is not your balance point. And then you can look at doing a 6-ton that curve. Now you still have your entire load that needs to be covered, and we're assuming that your entire load is going to be covered by that equipment because the doghouse is maintaining a temperature that system is able to provide that capacity you need to meet your load. If your capacity curve, as in this case, the 6-ton is below that correlating line, then you do not have a balance point with that piece of equipment. So you would need to look at something between a 6 and a 10-ton. Most manufacturers have an 8-ton. That might be a fit here. And that's where you have to refer to the manufacturer's design guides and engineering manuals to get this data. First, we're going to talk about supplemental heat as an auxiliary heat strategy. This is very common in areas where we don't get extreme cold. Namely, like my area, I'm in Spokane. We do supplemental strategy a lot because if we get cold, it's going to be cold. We're going to need some backup. But if something fails, it's not critical. Supplemental can get us by until we get somebody out to repair the equipment, and it's not life-threatening. This is a strategy to look at when there is no possibility of using a doghouse or that is cost prohibitive. Got heating while the VRV is impaired. Snow fell on it, damaged the outdoor unit, you had a catastrophic failure, whatever it may be, you're still getting a little heat, and it's not life-threatening to the occupants. You have some heating during normal defrost operation or catch up after a normal defrost operation, which most manufacturers, the default for defrost is that when you're in a single module, or in some manufacturers' case, multi-modules, the default logic is to switch off all the indoor units, switch the outdoor unit into full defrost, and try to get that defrost cycle over with as quickly as possible, and then get back to heating. Many manufacturers with multi-modules or multi-compressors also offer heating during defrost from the variable refrigerant system, but it is at a reduced capacity. So having some supplemental heat can help that system catch up in these times where you're either no heating or low heating, especially on days where you have a high loss because the temperature has gotten very cold. So as the temperature is dropping outside, the outdoor capacity is reducing. This is when you would bring on proportioned supplemental heat at the individual zones. The proportion of that total loss of that outdoor unit, you would proportion across those zones based off of their size. The proportion supplemental heater capacity should be less than the total zone demand because we're expecting that we're going to be getting some capacity out of the variable refrigerant system at that time. So how does this get controlled? It varies by manufacturer, but in the example of a ducted indoor unit, the ducted indoor unit would be the source that's moving air through the heater, whether that be an electric resistance heater added into the ductwork, a hot water coil, gas heater, etc. Typically, you're going to have a manufacturer's board that operates based off of logic on the unit that is going to allow contact closure when the fan coil is in heating thermal on, which means there's an active heat mode. It's integrated with the indoor temperature sensor or the wall controller, and depending on the manufacturer, it will switch on based off of a predetermined or preset temperature when the space falls below that point when actively heating. Also ends up referred to as trim heat, if you will. Now, not every variable refrigerant system, although very popular, to use ducted units these days. That's not always the case. Oftentimes you have high wall fan coils or ceiling cassettes, wall units. Everybody's got various different choices to meet the aesthetic or the space requirement, but not all of them can have an integrated heater added to them. So in the case of a high wall unit or a ceiling cassette unit that you can't add heat directly into, then you have to consider whether you're going to run a wall heater, small unit heater if aesthetics allow for it, baseboard radiators, either electric hot water. Any of those items can be triggered on in the same strategy that you would use for an electric heater in the duct. Same rules are going to apply. It's either a field installed accessory board added to the unit or points on a fan coil that can be programmed for the dry contacts to act. It integrates with the indoor temperature sensor or the wall controller, and the contact is able to close when it is in a heating thermal on state. It engages that secondary heat when the space temperature falls below a predefined set point. And again, this logic is all going to be specific to the manufacturer of choice. So on your typical curve, when you're plotting this, again, your load profile is the thing that is going to dictate where you're going to size your outdoor unit to determine your balance point. Your supplemental heat is going to be sized to meet the capacity up to that balance point. So that way, if there is a failure, you're not covering the entire load requirement, but you're covering enough of it. And that is why I say it's more mild cold climates that this is a common practice in. That reduces the upfront costs while still allowing some heat to be delivered in the event of a total failure. We're expecting that the variable refrigerant system will be running and it will be able to pick up the rest of the demand to finish out your load requirements. So given the load in this case, we're saying that this load is 90,000 BTUs minus 13. We're looking at this with a 10-ton nominal capacity outdoor unit. Your difference is, or your heater size total requirement in this example is going to be about 19,000 BTUs or approximately 6 kW. Total heater size, and this is where, again, you have to look at whether the juice is worth the squeeze. Is it better to have a larger condensing unit to reduce your heater size, or is it better to increase your heater size to reduce the variable refrigerant system sizing? For the amount of time that you're going to spend in that range, oftentimes the choice is the latter, that you're better off, it's better for the equipment to more right size that equipment and add that trim heat, increase the size of the trim heat, especially if you're going to put it on SCR style control, something that can modulate that. Again, we're assuming that you're going to have different heating requirements in each space. So in this example, we're looking at a total VRV system load with two fan coils connected to one outdoor unit. Excuse me. The nominal capacity in room A is 48,000 BTUs, and the nominal capacity in room B is 12,000 BTUs, and the connection index is the same based off of the model number. So formula to calculate the heater capacity in each of those rooms is the total heater capacity times the room connection index divided by the total connection index. When running that, the heater in room A would be 80% of your total heat, and the heater in room B would be 20% of your total heat. Probably the more commonly used auxiliary heat strategy is something we call alternative heating. This comes into play in much more in more extremely cold climates or areas where we want to have some extra safety. As the outdoor temperature drops, the outdoor capacity reduces, and at a given point, based off of fuel costs, electric costs, as that COP of that outdoor unit is dropping, it may become more beneficial to switch the heat source altogether over to something else. Or we've lost enough capacity, comfort's going to become an issue because discharge air temperatures are dropping. At that point, we shut the outdoor unit off and we switch over to the proportioned heater capacity at each individual zone. In that point, that proportion alternative heater capacity should equal the zone demand. This could also be defined as emergency heat. How to control this? It's very similar on the indoor unit side. In fact, most of the time you're running the same supplemental strategy on the indoor unit side, right down to the point where you say that it's more beneficial to switch over to gas or whatever other fuel source you're going to use. Similar to supplemental control, on the non-fan required units, the fan coil will switch to a low speed, so you're still able to get some filtration in the space on those wall hung units or ceiling cassettes. On the outdoor side, varies from manufacturer, but there's various ways to switch that unit off, either built into the logic, adding external boards with dry contacts that signal from an ambient sensor. You can adjust that set point locally, or you can also adjust it from the front end with a central control system with most manufacturers. Again, looking at that same load profile, you have surplus heating capacity of the VRV all the way down to your balance point. As that point crosses, you have a deficit of capacity if you were to stay with the standalone VRV system. Beyond your balance point, you're going to size your auxiliary heater to be able to handle the entire heat load all the way down to your design condition. That way, if there is a failure, the system is already entirely switched over either on the failure or at your predetermined temperature point, your balance point. Again, just to reinforce, you want that heater to be sized to handle the entire load when you're using alternative load and design temperature. Now, this happens most commonly, as I said, in areas where it is critical that we have some heat if there's a failure, or I've even had it happen where it is an application where the electrical cost to the building was fixed and they didn't have enough electrical to be running both the variable refrigerant system and the electrical backup. So we figure a point at that to switch over to full electric because the P is dropping to such a point, or the discharge temperature is dropping. It makes more sense to switch over to full electric at that point for the small percentage of time that we're going to be there. In this case, your total heater size is not going to change based on the VRV size. So you can still take a look at all those different VRV options, but it makes a lot more sense in this scenario to be looking at that. Doing a supplemental example. In this example, it's the same formula. This is a 3-ton in room A and a 2-ton in room B. You've got a 60-40 split at this point. So if you had a packaged gas unit that is going to kick in when you switched over, you'd split up those zones, deliver the capacity appropriately to each space. One of the other strategies out there is doing a dual fuel setup, either a manufactured option or through a third-party integration that most manufacturers have an option for now. This allows you to choose where your changeover point is easily through the system logic, change from heat pump heating or gas heating based off of temperature and utility cost benefit. This is great for multifamily central systems that you're going to be covering multiple rooms. It still allows to operate DX cooling and heating simultaneously when you're on the DX side of things. You can also run 100% DX heating operation as allowed down into that balance point. And once you get to that balance point, everything switches over to gas heat. Again, every manufacturer is going to have different logic for this, but all the manufacturers have some form of equipment to be able to operate in this fashion. Like I said, this is ideal for multifamily applications that already have a gas infrastructure or have a planned gas infrastructure, which most cold climates do. It allows you to optimize the system sizing based off of the balance point or the fuel cost in that area. In this example, you can see that they have a 5-ton. There's a couple balance points there, depending on the gas efficiency of the furnace. Right around 39 degrees on the higher efficient gas furnace and 34, 35 degrees on the lower efficient gas furnace. In this scenario, the heating requirement would be covered by the variable refrigerant system for the majority of the time. And once you got to your balance point, everything would switch over and gas heat would run to the coldest day of the year and then switch back over once it got above balance point. The next auxiliary heat strategy we'll talk about is doghouse. Now, this isn't used very commonly. I shouldn't say that. It is less commonly used because it does add costs to a project, but there are projects, especially in retrofits, that you can implement this strategy and have it make financial sense. For one instance, this is a case study in Canada that the customer had outdated condensing units that were being vandalized outside their building. They had a empty mechanical room inside the building that was surrounded by a conditioned warehouse, a heated warehouse, and this vacant mechanical room was on the outside wall. They were able to utilize that warehouse as a heat sink and implement the dampers to do a doghouse to put that equipment on the outside wall, use that space again, and reduce their overall install cost because it was already very easy to develop it. This keeps the space heaters out of the space. So if you're in wall hung ceiling cassette type situation, somebody does not want to see baseboard heaters or cadet wall heaters or small unit heaters. This gives you that option because you're only keeping the supplement going for the outdoor unit. This is also referred to as centralized supplemental. You don't have to proportion the heat. You don't have the added cost of each individual heater at the indoors. You're going to have a heater that is in the same space as the outdoor unit, and you're creating a fixed temperature operating condition for that outdoor unit based off your heat balance calculation. How it gets controlled is typically one status can control two functions. It's going to maintain the enclosure temperature, and the dampers will close below and open above the set point of that same control. You need to take into consideration in this appropriate means to drain the condensate out of the space. Typically, you're still operating down at a lower temperature that the system must take into consideration emergency and take into consideration emergency freeze protection for that condensate. Balance slightly different when you're doing a doghouse strategy. You're heating the outdoor unit to increase the capacity of the indoor unit. And your balance point is not actually the intersection, but where the capacity curve of the variable refrigerant system equipment correlates to your actual design load. An example of this balance point is 5 degrees on this piece of equipment. The enclosure temperature is above the balance point. We're not going to recirculate in that space. There is no load from the variable refrigerant system, and the heater remains off. We have a damper open for the condenser air to discharge out, or open for outside air to come into that space, effectively bringing the outside in. Once the temperature drops below the balance point, we go into a recirculation mode where we close the discharge air off of the condenser, we close the inlet air onto the enclosure, and we recirculate that air from the condenser. At that point, you have the loss of the space, as well as the VRV, the variable refrigerant system is going to add, pulling heat out of that space. And that's when the heater will turn on to maintain your temperature that was calculated in your balance point. So how does that balance point get calculated in this scenario? Use the manufacturer's data to calculate the balance point or the load for the variable refrigerant system. Typically, the designer is going to calculate the loss of the structure itself. From the engineering manual, you're going to look at your either kilowatt or BTUs, and then calculate your result. Your total heater capacity required for that enclosure equals the variable refrigerant load and the loss of that space. So total capacity, or your variable refrigerant load, is going to be your total capacity minus the power input. So if you were looking at it from kW, that would be 27 kW minus 9.57 power input, leaving you with 17 kW that you need to make up to maintain that balance point. Or if you did it in BTUs, 91,500 minus 33,000, you'd need 59,000 BTUs to maintain that balance point. There's also a shortcut by using manufacturer's software, and this would be if you needed a quick estimate. You could estimate based off of the available capacity known in the software, estimate the power input to be 20 to 30% of the total capacity. And in this case, that works out to about 61,000 BTUs, 89 times 70%. Like I said, this does happen in very, very cold climates. As I said, the juice is worth the squeeze at times. This is in Minnesota where they kind of get a little cold. This is West Health Transition Care Facility. It's 100 tons of condensing unit with 75 fan coils. And you can see in this scenario, they didn't do exactly what we showed in those images where you're discharging through ductwork off of the condensing unit because the piping and the ceiling height was prohibitive to that. So what they have instead here is the damper wall and then some large propeller fans blowing out on the other side. So they're achieving the same effect with large fans instead of discharge using the fans off of the condenser itself to discharge out of the space. Another one in Minnesota was a retrofit of an old hotel that wanted to switch to a variable refrigerant system, but they didn't have a lot of space to put these units on rooftops around there, and they had 24 stories to deal with. So they opted that the juice was worth the squeeze to build a penthouse mechanical room and put all of the condensing units up there and do a doghouse on the top of the building, serving everything down below from above. So finally, the other common way that has been happening for a little over a decade now, I think, is enhanced capacity variable refrigerant systems. These are systems that are designed specifically to operate in cold climates and do so better than their standard efficiency counterparts. So the low ambient systems allow for increased heating performance, as you can see by the charts there, typical 6-ton, 8-ton, and 10-ton, anywhere from 40 to 60% more capacity at -13 than their standard counterparts. These allow vastly improved heating in cold climates, up to 100% of your nominal rating at 0 and up to 85% of nominal at 13, up to 60% of nominal at -22. Now you would think that these are going to be grossly oversized, but it is actually technology driven that is allowing these to provide that amount of heat at that lower temperature without being grossly oversized on the cooling side. Performance on these is going to be specific to the manufacturer of choice. Heating with some manufacturers down to -22 is standard, and cooling up to 122 is standard. And the way they're getting there with these is with some new technologies that have been added over the years. One of those is cooling the inverter circuits with the refrigerant circuit. This allows to completely seal the electrical area, which through practice was learned that light, dry snow can suck up into electrical components, and when the temperature warms up, miraculously things short out and break. So this allows for better sealing of the cabinet and protection of the electrical components without any influence from the ambient temperature or the ambient environment itself. New compressors have been added over the years, vapor injection compressors, which allow an improved discharge temperature by capturing waste heat off of the indoor coils and re-injecting it back into the compressor to increase the discharge temperature, adding capacity, as well as improve discharge temperatures off of the fan coils on the inside. Improved heat exchanger efficiencies with multiple row coils to maintain smaller footprints, and more heat exchanger surface with most every manufacturer now running a 4-sided coil. The other thing that has been added over the years is many manufacturers are using a hot gas defrost circuit to heat the lower portion of the coil in the pan to aid in defrost water shedding without having to add additional resistance heat to the outdoor unit. All of these features have been added to enhanced capacity systems to optimize the total life cycle cost of the system and allow more flexibility in design for cold climates. So just in review, ways to approach low ambient climate design. Supplemental is probably the first go-to in most of the mild or cold climates. Alternative is, in my experience, the most commonly used. That way you have both supplemental and the ability to switch the entire system off and switch to an alternate fuel source or switch straight over to electric. Dual fuel applications, either through manufactured strategy or third-party integration DX kits, or doghouse, locating the air-cooled units inside. And most recently and more commonly these days is, if the environment allows for it, 100% air source, low ambient systems, or the enhanced capacity systems. With that, I want to thank everybody for your time and see if anybody has any questions about what we covered today.
Thanks, Mike. If anyone has any questions, please unmute yourself. Or you can also type in the chat box. I have a question, Mike. So what was the most common low temperature scenario that you ran into with these applications?
Most common problem?
Yeah, most common problem.
Most common problem is failure to deal with the defrost shed. And allowing, even if you have the ability to get the defrost water away from the unit, if it's not with outside of the unit, you can still end up in a frost pinch situation that crawls up around the outside of the unit.
Okay, that makes sense.
Most common comfort concern is from grossly oversizing, that you end up with short cycling, overheating, and overcooling spaces.
It's like I don't see any more questions.
Thank you, Zach and Thomas.
Yep, thank you, Mike.
Thank you, everyone. Appreciate your time.